Okay, this is the second segment of an introduction on information theory. And in this segment, we'll talk about how to quantify information. And as we described last time, basically, the way to quantify information is very much related to the problem of compression. Because, for example, if we have two parties, let's say Alice and Bob, and let's say Alice knows some piece of information or a message X, and the amount of information of message X will be equal to the minimum number of bits needed to send from Alice to Bob to convey that information. So it's kind of an intuitive way to see things, right? So, or like the amount of information in X will be simply the minimum number of bits needed to represent X. So we mentioned that there's many ways to interpret this. Even we have this picture here. We have the Komogao wave is basically thinking like to convey this information is trying to write a program to convey that. So we have the Komogao capacity. And instead in this class, I'm also in the area of information theory. Most people will take the view of Shannon and basically see things stochastically. So in a sense, every message will be just a outcome of a random variable. So let's say X is just a random variable. And also, let's consider a more concrete example. Let's say X is basically outcome of flipping a coin, so X can be either head or tail. So for this specific example, how many bits will be needed to send this message X from Alice to Bob? So I hope you guys will agree that we only need 1 bit, because there will be two outcomes, head and tail, and 1 bit will be sufficient to represent these two values. And by the way, here we are assuming the coin is unbiased, so in the sense that P head is equal to P tail. So we'll consider the case of bias with bias coin and the case that is non-uniform random variable just a bit later on. But for the moment, let's stick to the random variable that they are all uniform. That basically all the outcomes have the same probability. And let's look at another example. Let's say I have another random variable, let's say y, and y is the outcome of throwing two dice. Okay, let's thinking like outcome of flipping 2 coins. Let's start with this example first. And then therefore like there will be like 4 possible outcomes, right? It can be head, tail, head, and tail. Or how much information will be in this variable y here? So I hope you guys will say that there will be only 2 bits, because I can have 2 bits that can be able to represent all these 4 values. Because I have 2 to the 2 is equal to 4. So I hope from these examples I can kind of convince you that if I have a random variable, let's say Z, and if it has kind of n different outcomes that they are all uniform, let's say outcome A1, A2 up to AN, then the amount of information for this random variable will be simply log base 2 of n. So far so good. Here we only considering the amount of information for each random variable, or like for each event. So somehow actually we can also interpret like what's the amount of information from each outcome of an event. For example, if we go back to this example y here, I would say that for each outcome that will have 2 bits also for the amount of information for that outcome. So first of all, like, I know all these should have the same amount of information because the problem is basically symmetric, that all these outcomes are equally likely, therefore there's no reason to believe that one outcome have more information than the other. And secondly, I know that the average amount of information among all these outcomes should be equal to 2 bits, so therefore the individual outcome should have the amount of information equal to 2 bits also. And what is that 2 bits is coming from? So for each of these outcomes, the amount of probability of this outcome is equal to 1/4 way. And that 2 bits is exactly coming from log base 2 minus log base 2 of 1/4. Or another way to think of that is, if I have an outcome that have probability p, then I can imagine that this is like have the same similar outcome that is from another random variable, but that random variable is equally likely, and therefore that random variable will have 1/p so many different outcomes, and therefore the amount of information for that random variable will be log base 2 of 1/p. And because all the outcomes there are equally likely, so the amount of information for each outcome will be log base 2 1/p as well. Therefore it's just equal to this here minus log base 2p. So okay, I just want to kind of put a disclaimer here. The argument here is not really rigorous, but I just want to give you an intuitive reason why the Shannon entropy have a formula as shown in the following. I hope that this gives you some intuition that at least it will help you a lot just to memorize what is the Shannon entropy. We'll give like more rigorous argument later on. Actually, we'll at least have 2 more arguments why the Shannon entropy will be like that. But in any case, because like for each individual outcome, I can claim that the amount of information is log 2 base of p. Let's say if the outcome is x, the amount of information is minus log base 2 of px. So therefore, the average amount of information for that random variable x, here I will use the notation hx here, will be equal to the average of that way, average of minus log base 2 px here. Be careful, I am using the convention that big letter represent a random variable and small letter represent a realization of the random variable. And this is equal to px log 2px sum over x. And this is exactly the Shannon entropy. Actually, this is a funny story about like why Shannon called this thing entropy, and apparently he had consulted with von Neumann, and von Neumann told him that like actually before he talked to von Neumann, he was thinking to call entropy as like information content, but von Neumann just convinced him that like first of all, in statistical physics, they already have a very similar expression and known it as entropy, therefore you should use entropy. But more importantly is, at that time, really no one knows what entropy is. Like, statistical physics is not really that common. And he said that like, if you get into an argument, you will always be advantage if people don't know what you're talking about. So, but I guess it's kind of like an urban legend, I guess. So, anyway, in the next segment, I will give a more rigorous argument of why Shannon entropy is given by this expression.